So we were doing SGD and convergence. And we have done this for L-max smooth and sum of convex in the last class. So that was theorem 5.7, and now we will do it for PL and smooth. Okay, so this is convergence for PL and smooth functions. Okay, so so in this 5.9, in this we assume sum of L-max smooth, and F is mu PL for some mu greater than 0, and we consider the iterates xt, and these are generated from SGD. Generated by the SGD with constant step size which is 0 less than gamma less than equal to mu by LF L max. Okay, then in this case we can prove that Fxt minus Fx star is less than equal to 1 minus gamma mu t and Fx nod minus Fx star plus gamma LF L max by mu del star F. Okay, so this is similar to what we had before, but here if you see the terms for the strongly convex and smooth, so in place of strongly convex we have now mu PL. Okay, so as you know, mu PL is a class which is bigger than the strongly convex. Okay, so hence with this theorem you can cover slightly more general functions which may not necessarily be convex. Okay, so in fact we had one paper recently in SIAM Journal of Optimization. It got accepted like I think 5 days ago, and there we had to assume PL as well, and we saw a lot of applications there. Okay, in GANs also we have applications there. There's like 4 or 5 applications there. So and these theorems are also recent. Okay, so usually you will trace these theorems to 2021, 2 years ago, 1 year ago. So these are kind of latest results. So let us see a proof of this. So X obviously is argmin in argmin of F. So that sigma star F is variance of grad Fi X star. So this we know. Okay, the sigma star F, this is from the lemma 4.17. So we will expand the squares in yeah, that's fine. Okay, I mean, do we really need that? Okay, the first line I will be keeping it on hold. So let us so since we have sum of L max smooth we have that F is LF smooth. And then we can use the lemma 2.25. So we can use lemma 2.25. So recall lemma 2.25. So let us recall lemma 2.25. So this is F from RD to R, L smooth. Then for all x, y in RD, basically it's a smoothness condition. So Fx plus grad Fx y minus x plus L by 2 norm y minus x. So this is the smoothness condition that we know. So we want to use this with the fact that F is some LF smooth. So with this, the choice of y will be xt plus 1, let's say, and then x will be xt. So in that case, we have, so let us put this in a box. This is a lemma. So then we have f xt plus 1 is less than, because we are just following that, xt plus grad f xt plus 1 minus xt plus lf by 2 xt plus 1 minus xt squared. So we have just applied the lemma 2.25 with y equals to xt plus 1 and x equals to xt, okay, and with the Lipschitz constant LF. So the statement we have to prove is this, like the difference is bounded by this. So one thing we know is xt plus 1 and xt, they are related via SGD. So we can substitute that xt plus 1 minus xt, we can substitute this as grad f xt, okay. So we can do this in the second term as well as the third term, okay. And we have the gradients, and the usual trick that we are doing again and again, and from the gradient we use the variance transfer, okay, go back to function values and so on, and that's how we want to go there, which is everything is in function values here. So the first step is get these guys into gradient and then do variance transfer, okay. So let us do this. So so this is equal to f xt, because xt plus 1 minus xt is minus gamma grad f xt, so that's why there will be minus. So I will keep that minus outside, minus of gamma grad f xt comma grad, but this is the stochastic gradient, right? So this was for the ith sample, so there is a sub I there. So grad f I xt plus lf by 2 norm of, the gamma was there and then there is a norm squared, so let us keep gamma square outside. So let us keep gamma square outside, and inside we had grad fi xt norm squared. I believe we will do gradient transfer. That's the trick to go from transfer gradients to function values, right? So I believe that's will be the step. And the fact that we have these stochastic gradients, we are supposed to transfer them as well to f. So we are supposed to take expectation as well, and we will take it conditional on xt. So we will touch these grad fi, which are the random variables here. So after taking expectation, conditioned on xt, and then yeah, I mean we will do variance transfer, but that let us do that as the next step. So first let us do this expectation first. So this will be expectation of, yeah, so expectation will apply here, as I said also in the previous analysis, because if xt is given, meaning here we say that it's conditional on xt, meaning that xt is given, then of course xt is no longer a random variable, but xt plus 1, which is obtained via xt minus grad minus gamma grad of xt, grad fi xt, which is a stochastic variable, random variable. So hence xt plus 1 remains random variable. So expectation will apply here. Okay, and so inequality remains maintained by expectation. So we have fxt is not a random variable because xt is known, and minus gamma, also grad fxt is a deterministic quantity. So but expectation will go inside here. Okay, of course it doesn't go here, but it will go here. So let us do this as an initial step, and if it goes there, expectation of fi, we know that it's grad f also. Okay, so we have seen this also in last class. So grad f xt, and this is expectation of grad fi xt plus lf gamma square by 2 and expectation cannot go inside norm. Okay, so expectation will be outside the norm. So expectation of norm of grad fi x, why do we write t sometimes down, right? It should be always up. It's the iterates are usually written up. So okay, that's why I said, right, you see this once, after that it looks familiar. And okay, and then we are supposed to do variance transfer. As I said, this becomes this, because expectation of fi's are is nothing but gradient of xt. I have proved this in the last class as well. So this becomes norm of grad f xt squared. Okay, so this is equal to now we will apply as a next step variance transfer, because we don't want to see these gradients, right? In the theorem we didn't had. So we know the trick to transfer gradients to function values via gradient transfer. So okay, so now we will do variance transfer. So if we do a variance transfer, then variance transfer told us that expectation of norm fi is less than equal to, so we will recall variance transfer. Okay, it's like it's good to keep writing so that you kind of memorize at some point. Okay, so this was lemma 4.19. This was variance transfer. So just keep writing it, like repeat it, just for, yeah, so recall this. So variance transfer, and this is for sum of L max smooth. So F sum of L max smooth. Then it says that you can transfer the variance, which is in this case is norm of grad Fi x, and this is dominated by 2L max Fx minus Fx star plus 2L max delta star F. Okay, so let us put this in a box. This is we are doing a recall of lemma, and we will apply this now, and we will apply this in the last term. Okay, that's where we have this grad Fi. Okay, so we apply it here. So if we apply it there, then let us see the terms. Okay, so we will keep the second term untouched for the moment. Let us do only this one. Okay, and this will be, this is dominated by this, so we have further less than equal to. So this is less than equal to Fxt minus gamma grad Fxt plus gamma square Lf L max Fxt minus Fx star plus gamma square Lf L max delta star F. So this is the part that we got from the variance transfer. There was 2 already in the variance transfer, so 2 got cancelled. So we got that Fxt term, right? The second term still involves a gradient, right? So we will try to remove that as well. And we have to, so we are supposed to use the PL, right? And PL relates gradient to function values, okay? So that's where that gradient will be removed by using the PL condition, because this proof is on the PL. So let us now kind of recall PL condition. So in the PL condition, we what it says is that for all, so F is mu PL if it is bounded below and it satisfies Fx minus Fx star is less than equal to 1 by 2 mu norm of grad Fx whole squared. So this gives an upper bound, and for this gives an upper bound, and fortunately what we needed with the negative, so that seems to work out, because if you multiply with minus throughout, then minus of this guy will be less than equal to this. So this seems to work because we are looking at the upper bounds. So then we are going to substitute this now. So let us put this in a box. This is so this is further less than equal to Fxt plus gamma. Yeah, there are some as a one more step we have taken so this will be applied for xt, okay? So this is Fxt and this minus Fx star, and there is also Fxt minus Fx star. So what I will do is that I will take the common also and rearrange all the constants. So that's what I'm going to do it now. So gamma L F L max minus 2 mu, and then this is fxt minus fx star, and plus the remaining terms LF L max delta star f. So we have taken that common, fxt minus fx star, and we have done some rearrangement here, that gamma we took it out, and so there should be a region there, right? So in the condition, there may have been some conditions, gamma L max, gamma L max, okay, or not this one, okay, so gamma LF L max is less than equal to mu. The step length was such that gamma was less than mu by LF L max. So this was given in the theorem. So step length condition was like this: mu by LF L max in the theorem. So this guy comes here, gamma LF L max is less than equal to. So overall it will be kind of minus mu. So that's less than equal to mu, and then there is a minus 2 mu, so it will be minus mu, so minus gamma mu, right? So let us, so this is fxt plus, or this is like minus gamma mu now, minus gamma mu fxt minus fx star plus gamma square L max delta star f, and this is because gamma was less than equal to mu by LF L max. Okay. So this inequality was because of this, and furthermore mu gamma is less than equal to 1. Okay. So why is that, right? So mu gamma is also less than equal to 1. Okay, I think at some point we have proved that mu is less than equal to LF. So mu is, the mu of the PL that we have is less than equal to the Lipschitz constant LF. Okay. So mu is less than equal to LF, and LF itself is less than equal to, so basically, so if I multiply by gamma on both sides, okay. So what we are supposed to prove is mu gamma is less than equal to 1. What we know is that mu of the PL is less than equal to LF, and this is less than equal to L max. So combined with this and this, we are supposed to have mu gamma less than equal to 1. So let us say that we multiply by mu, okay, there will be mu square, right? Okay, anyway, so this would imply gamma mu is less than equal to mu squared by LF L max. Okay, then it makes sense, right? So mu by LF is less than 1, mu by L max is also less than 1, so overall it's less than 1. So this, I can see this as mu by LF times mu by L max, and each of them are less than 1 according to this. So overall mu gamma must be less than 1. So we have, so this is from the step length, that mu less than gamma less than mu by LF L max, and the fact that mu is less than equal to LF is less than equal to L max. So this implies gamma mu is less than equal to mu times mu by LF L max. So this is less than 1, since mu by LF is less than equal to 1, and so let us say put this less than equal, and mu by L max is less than equal to 1. Okay. So all this, it seems that all this means that we will drop that t term, it seems. Okay. So are we doing that? And since we want also fx star, so okay, I'm thinking what is the role of proving this, because we are not dropping this immediately. Maybe we will see at the next. So the next step will be we subtract by fx star on both sides, because we started with fx t plus 1. So subtracting f x star from both sides. So then we have, and then we will take the expectation. So then we have expectation of fx t plus 1 minus fx star, and this is less than equal to, and since we have subtracted fx star, so there will be one fx t minus fx star here, and there is already one fx t minus fx star here. So taking common, we will have 1 minus gamma mu, and then I believe we will do the dropping. Okay, so then so this is less than equal to 1 minus gamma mu and fx t minus fx star, and then plus the constant terms is gamma square L max delta f star. Where did I miss? Okay, there is we have missed the LF as well. Okay, so there is LF. Okay, so there also we have missed an LF term. Okay, and remember that in the theorem we have to go down to fx naught. Okay, so here we are supposed to bring fx naught. So we will apply this recursively now, and there will be. So we have taken expectation. So I forgot to put expectation in the here. So this is not the condition expectation now. This is the expectation on everything. Okay, so hence it applies also to fxt. So then you see this recursive structure here. So fxt plus 1 minus fx star is given in terms of expectation of fxt minus fx star. So basically you keep applying this recursively. So now you substitute, replace this guy by the same formula. So you will keep getting this power, and this will start multiplying here also. So applying this recursively, so recursively so if we apply recursively, then we should get until fx naught, which was in the theorem. Then we get e of fxt minus fx star is less than equal to 1 minus mu gamma t expectation of fx naught minus fx star plus gamma square LF L max delta f star. So basically the last term you will see here will be like it will produce a geometric series for the last term. Okay, because each time this comes up with this guy and this comes up as an addition, right? So there will be sum of geometric series with this here. So this is gamma square this, and then 1 minus, so this may not be captured here, so let us do this here. So this will be j equals 0 to t minus 1 minus gamma mu to the j. Okay, and for the geometric series we have 1 minus gamma mu to the I I equal 0 to t minus 1, and this we apply the geometric series formula. So this is t by 1 minus mu gamma, and this is less than equal to 1 by mu gamma. So if we substitute this, then we have that last term which will be less than equal to 1 by mu gamma. And overall, what was the theorem? So theorem 1 by mu gamma, and then there is a gamma square above. So gamma gets cancelled. So we get exactly the statement of the theorem. Okay. So that's it. Okay. So you substitute this guy by less than equal to this, cancel out the gamma, and that's the final statement of the theorem. So what we have done is took the gradient just for a sample, but what is common is mini batch SGD. Okay, mini batch you take some batch of samples. So the analysis that we have done is actually very pretty much similar. Okay, so just for the mini batch SGD, we will complete this remaining part, and then we will go to momentum based methods, okay, which are more like robust. So for mini batch SGD, so in mini batch the gradient is defined over a batch. Okay, so the way it's defined is like this. So at the point xt, you compute a gradient on a batch of the data rather than one data point or one sample. You will compute on the batch. So this is defined as 1 by, so this is the batch size, sum of gradient of fi xt and sum over all the samples in the batch. Okay, so this is called so SGD with taken as this as a gradient is called mini batch SGD. So mini batch also includes the case where we took only one sample. Okay, so that will be a special case of that. So the algorithm for mini batch SGD is x naught, let us say RD, and let a batch size be one of these. So there are, let us say, n samples, then mini batch size could be one sample. You can take two sample. If you take all the sample, then it becomes a full gradient method. Okay, so basically it becomes gradient descent. But in machine learning, usually n will be, let us say, in several 100,000, let's say, in realistic data, or it could be million of the samples. So by the time you compute the gradient for this million samples, it may be too late already. And so usually you will go with this stochastic method, that you will compute it for small batches, which is cheap. And there are also reasons of generalization where computing stochastic gradient is sometimes generalizes more. Okay, prevents overfitting and so on. So this is the mini batch algorithm where the iterates xt. So basically you choose this bt, which is subset of these. So you will pick randomly a batch bt of size order of bt. Okay, so again it will be random. It is still called SGD because the samples you choose in a batch are also random. So xt plus 1, the update is very similar, minus gamma t grad bt. So grad f, this batch, right, grad f bt xt. So we will assume that these batches are sampled uniformly. So meaning that the probability of picking a batch will be 1 divided by number of ways I choose the batch. So n choose b. B is the small b is the batch size. So so the probability of picking a batch size of size b will be 1 divided by n choose small b. Okay, so batch is assumed to be sampled randomly with probability one by n choose b. Okay, so this we can also write this in the form of n minus b factorial by n factorial, n choose b. So so in that case, the expectation of the mini batch gradient will be grad f b x, which is 1 by n choose b, and then sum of grad f b x and b over 1 to n, and size of b is b. So if we compute the expectation, then in this case the expectation of this will be like this, and the note says that it's an easy exercise to verify that this is actually gradient of f. Okay, so it is an easy exercise that it is gradient of f. Okay, so maybe we should leave this as an exercise. So one of the good things about mini batching is that it can help you in terms of, let's say, parallel computing. So in the sense that since you have now batch of size b, let us say, then each of these gradient calculations can be done parallelly for all I in capital B. So so these computations over the batches can happen in parallel, okay, depending on how much parallel resources you have. But in the single case, you cannot do that. In single case, you pick an I, compute the gradient, and then you pick another I. Okay, you do the update, then you pick another I, then compute the gradient and do the update. Here, you are supposed to do it sum or all b. Each of the sum are independent. So you do this, each of these gradient computations for each of these independently. That can happen in parallel. Okay. So, and we have similar concepts like we had for the single sample case. We have same ideas of mini batch gradient noise. So let us. So we have similar concepts of. So this is definition 6.3, and so assume sum of L max smooth and B in n. So choose one of the batch sizes. As a special case, you can choose B equal to 1, but then everything will become like what we did before. Okay, so B equal to 1 will be not very interesting for us because we want to generalize now. So we define the mini batch gradient noise as a similar way, sigma B star define infimum of x star arc mean of f VB grad FB x star. The difference is that the variance is taken over the random variable b, capital B, okay, and this is sampled uniformly across the subsets of size B. If you are looking for variance with B, then you take those batches of size B. Okay, if you want to change the size, then you have to change it here. Then you will get a different sigma star. So it does depend on the B. So first you fix the B batch size, and then you collect those batches, okay, and you compute the variance over that. Okay, so and we can also define in this case LB smooth, where B stands for this batch size. So this is definition 6.4, and here again we assume sum of L max smooth and B in one of these, and we say that F is LB smooth in expectation if for all x, y in Rd we have 1 by 2 LB expectation of B grad Fi y minus grad Fix norm squared is less than or equal to Fy minus Fx minus grad Fx y minus x. So this is LB smooth in expectation. Similar theorem what we did for single sample, and that will conclude the SGD as a full thing. So we did for single, we did generalize this for the batch, and the analysis is very similar. With this now changes in these, the gradient noise is now like this, and the smoothness is given like this, but other than this it's very similar. So we want to wrap up that mini batch analysis full scale. These are the one of the lemma that we will need is lemma 6.7, and this is sum of L max smooth and sum of convex, then expectation of B grad FB x norm squared is less than or equal to 4 LB Fx minus infimum of F of the usual way is Fx star, and plus 2 sigma B star. Okay, so this is a lemma. We will not prove this lemma. We will skip this, let's say. Okay, we will just do this main result. We will assume that this lemma can be done. So we will write the main result, and as I said, it's exactly similar to this. It's just that LB appears. This LB appears. So I will write this statement here. So now that's the main result of mini SGD. Okay, so the main theorem, the final theorem of, so this is convergence for convex and smooth function, and this is for mini batch SGD. Okay, so the statement says that this is the theorem 6.8. The statement assumes sum of L max smooth and sum of convex, and consider the xt which is the SGD kind of the SGD iterates generated by mini SGD with a step size is 0 less than gamma t and less than 1 by 2 lb. Okay, and then we have this bound on fxt and fx star. So then it says that expectation of f x bar t minus fx star is less than equal to norm of x naught minus x star squared divided by 2 sum of k equals 0 to t minus 1 gamma k 1 minus 2 gamma k lb plus, okay, if you recall the previous single sample case, you can recall that it's exactly the same, okay, exactly in the sense like just the constants are a bit changed. Sum of k equals 0 to t minus 1 gamma k 1 minus 2 gamma k lb sigma b star. Okay, so as you can see, our arguments for the step length and all this will be choice of the step length will be similar here also. We will still want the step length to be sum to infinity and the square of that is finite. The changes that you see are mostly here. If I remember correctly, it seems like this is the only change, or this also. Okay, so I believe this is the only two changes basically. L term seems to change and the sigma star b term seems to be changing. Okay, otherwise everything is the same. So that's why the case that we did before, the proof also is like very similar. Okay, so for completeness I will do that, but we will do it quickly. Okay, so it's like I think 10 lines we have to write. So let us do that. So let's see, like from the single case, how did we extend this to the. So let us, as usual, assume that x star is the argmin of f, and then we have sigma star b was defined to be variance of grad f b x star, and like before we will start looking into xk plus 1 minus x star. So we will add and subtract xk. Okay, add and subtract xk, and xk plus 1 minus xk will be replaced by the gradient SGD, the mini batch gradient. So these are the steps we will do, and then we will be left with xt minus x star. So let us do this as a first step. So we have xk plus 1 minus xk plus xk. So we add and subtract, and then this is x star whole squared. So we pair this with this and this with this, and apply a plus b whole square formula. And if we do that, and ideally like we are supposed to replace this by grad f xk as well. So this is equal to xk minus x star minus 2 gamma k grad f bt xk minus x star plus gamma squared grad f bt xk norm squared. So you can see clearly we have done this thing so many times. So a plus b whole square formula and xk plus 1 minus xk replaced by grad f bt. Okay, so we have done this many times. So now, since we are doing this many times, now we get the feel, right? So now we suspect that there will be gradient transfer for this guy. Okay, so because usually we don't want to see grad in the final bounds. Okay, so that we will do that. And but even before that, one of the troubling thing is this guy, which is in terms of the mini batch. So we want to see the usual gradient. So to get rid of this, we will apply expectation now, and we will make this, after applying expectation, it will become the usual gradient, right? So that these are the things we are supposed to do. So we will do expectation condition on xk. So taking expectation conditioned on xk. So expectation will apply here because xk plus 1 will be random variable. Expectation won't apply here. Expectation will apply here. Expectation will apply here because these are random variables. Okay, so if we do that, then we have, so we are supposed to take expectation. So if we do that, then we have EB of xk plus 1 minus x star whole square. It is conditioned on xk, and this is equal to xk minus x star whole squared plus 2 gamma k grad f xk comma x star minus xk plus gamma k squared EB norm of grad bt. So f bt, grad f bt of xk norm squared conditioned on xk. Okay, remember I have applied expectation and I have already written grad f xk there. Okay, so and as usual, our plan is to now do variance transfer for the norm of the grad f term. So they will do that. So doing variance transfer, so if we do that, then we have EB norm of xk plus 1 minus x star xk, and this is xk minus x star plus 2 gamma k grad f xk x star minus xk. So variance transfer only works on the last term, and if we do the variance transfer, then it will be so the variance transfer that we had, which for the mini batch I said that we will not prove, right? So that was lemma 6.7. So I just stated that, and I did not prove that, but we will use that lemma variance transfer for the mini batch. So we can do that as an exercise. So that says that so recall lemma 6.7. So in this was the variance transfer that said that EB of grad FB x is less than equal to 4 LB of Fx minus infimum of F plus 2 sigma B star. Okay, so we recall this variance transfer in the mini batch case. So that will help us replace the last term. Okay, so we have already written up to here. So we can write it straight away. Okay, so let us, I will drop that, and but let me do that here. Xk plus 1 minus x star given xk is less than equal to xk minus x star plus 2 gamma k grad f xk x star minus xk, and the last term was this guy, so this is plus 4 lb fx, so x in place of x we have xk, so xk minus f x star plus 2 sigma star b. So this, maybe you can just remove this because this was incomplete. So we just follow like this now. So we do variance transfer, we recall variance transfer, and now we continue from here. So just the last term was now replaced by variance transfer. And this guy also, as you can see, in the bounds we don't see gradients, but then you have to see what was given in the theorem. In the theorem it was given convexity also. So first order definition of convexity will be used here. Okay, fy greater than equal to fx plus grad fx y minus x. Okay, so that's the first order definition of, so we will use that to get rid of the second term now. So now we will apply the convexity. So using convexity of f, so the convexity, as I said, so just first recall first order convexity. So fy is greater than equal to fx plus grad fx y minus x, and this is true for all x and y in the domain of f. So in our case, when you have to use this inequality, always look at what is with the gradient, because everything else gets fixed, then you are not confused. Okay, so when I have to use this, I always look at here. Okay, what is this? Xk. Okay, then y must be x star. Okay, so in this case we will take x to be xk and y to be x star. So with this we will apply, so we are looking at the upper bounds, right? Okay, and fortunately there is a sign thing. I was wondering what will happen because I'm looking at upper bound and this seems to be lower bound. I was a bit worried, but I'm not, because there is a x star minus xk. So when I flip, there will be negative, which is what I want. Okay, so then with the consequence of this, we can write like this, grad f xk, and then x star minus xk is less than equal to f y was x star minus f xk. So this is the consequence of applying this with y x equals to xk and y equal to x star, and I have to look there. So there what I am given is grad f xk x star minus xk. So I will multiply by minus on the both sides. So if I multiply by minus on the both sides, these guys get flipped, k minus x star, which is exactly what I wanted, and here I will have a minus, here I will have a plus, and obviously this gets changed. That was also it is already x star minus xk, right? But no, one second. No, if it is x star minus xk, but we need a lower, no, it's it's already less than equal to, right? Okay, okay, and this is xk, it's already in the same form. Okay, so I'm just wasting your time. So this is grad f xk and x star minus xk, and this is already less than equal to f x star minus f xk. Okay, yeah, these stars and k sometimes are not very clear from a distance. So grad of xk, and we just substitute this, and so continuing from there. Okay, so let us, so we continue, then it is eb xk plus 1 minus x star given xk is less than equal to norm of xk minus x star, and plus, so there is 2 gamma k, so that goes with this guy, and maybe we can collect, okay, there is a minus there, so 2 gamma k, what is the good preference, right? Xk minus x star or x star minus xk. Usual preference should be xk minus x star because it's a minimization problem, so we want to keep things positive. So let us collect in the form of xk minus fx star, so then this guy will be made negative. So basically it means 4lb minus 2 gamma k. Okay, so 4lb minus 2 gamma k, this goes with f xk minus fx star. And then plus 2 sigma star b term. Okay, let us keep track that we are not lost. So sk minus fx star is fine. 2 gamma square we have missed somewhere. Okay, we are indeed lost, it seems. So we applied the convexity, that's fine. So convexity has been applied, but we missed gamma. Gamma was missed from above, but it seems like there were 4 gamma square term with one of these guys with the LB. So with the LB we are missing missing some gamma squared, right? Okay, yeah, this guy. Okay, got it. So this one, this gamma k square we are missing. This was, this we applied on this only, but then this gamma k square was missing. So this gamma k square is there. I guess that's the only thing we are missing. So here will be gamma k squared, but the way they have written is 2 gamma k, 2 gamma k, so that there is some relationship here to be exploited. So let us say this is plus 2 gamma k out, and then 2 gamma k inside. Okay, so now it seems okay. So norm of xk minus x star squared plus 2 gamma k lb minus 1. Oh, okay, minus 1. Okay, because 2 gamma k is now taken out, so this guy has to be now just 1. And then fxk minus fx star plus 2 gamma k square is missing here also, because the gamma k square was also supposed to be here. So this was gamma k squared. So since in the theorem the statements are given, I believe statements are given in terms of fxk, so we want to keep it on the left hand side and put everything on the right hand side, and then do some simplification. So basically 2-3 lines are left, so let us do that. So rearranging, okay, let us do this here. Okay, and so if we do rearranging, basically by rearranging we mean that we keep this on the left hand side and everything on the right hand side. So if we do that, then we have 2 gamma k 1 minus 2 gamma k LB and fxk minus fx star. This is less than equal to, let us see here. So it's less than equal to norm of xk minus x star. So this is xk minus x star whole squared and minus of the expectation was there. So norm of xk plus 1 minus x star squared and then plus 2 gamma k squared sigma star b. So we have just done a rearrangement here and that expectation is the conditional one. So that's understood. And we will take an expectation again. Okay, it's a similar pattern to what we did before. So now we will take expectation, taking, now it will be a generic expectation, not conditional. Okay, so taking expectation, then we will have expectation there. So then it will be 2 gamma k 1 minus 2 gamma k LB expectation EB and then fxk minus fx star is less than equal to EB of norm of xk minus x star whole squared minus EB of norm of xk plus 1 minus x star plus 2 gamma k square sigma star b. We just done expectation here. And you can see what is coming next. We want to go down to x naught, right? And we see some telescopic sum and cancellations going on here. Okay, so for instance, you can keep running for the k. So basically you sum over k. So if you sum over k, so there are like two things we see. Sometimes we do recursion to go until the k, and then we have some geometric sum and things like that. Those things happen when you have strongly convex mu PL, and in these cases usually you have this difference type, and while you are going to the x naught, this intermediate one gets cancelled. Okay, so this is called telescopic sum, meaning only the endpoints remain. So if we do that, so summing over k equals to 0 to summing over k equals to 0 dot 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 t minus 1, and using telescopic cancellations. So this gives 2 sum gamma k 1 minus 2 gamma k LB EB of fxk minus fx star, and this we are summing for k equals to 0 to t minus 1. So and then due to the telescopic thing, only endpoints of that difference will remain. So we will be left with norm of x naught minus x star minus EB of norm of xt minus x star plus 2 sigma b star, and then sum of gamma k squared k equal 0 to t minus 1. Okay, verify yourself that everything is correct. Since the first one, x naught minus x star, went down to x naught minus x star, it became x naught and x star are no longer random. So expectation was removed from there. But in the second one, we have xt minus x star. So xt remains a random variable. This is a generic expectation here, not condition now. So xt, it will treat it as a random variable. So that expectation remains. So then we will divide by this. Okay, this is similar trick we have done before. Okay, we divide by this. We want to see this, and then we will use the Jensen's inequality, if you recall. Okay, so just 2 lines now. So first we divide by this, dividing both sides by by 2 gamma I 1 minus 2 gamma I L B I equals 0 to t minus 1. So if we do that, then we are left with just so here we are left with EB, and then gamma k 1 minus 2 gamma k LB divided by sum I equals 0 to t minus 1 gamma I 1 minus 2 gamma I LB, and this is fxk minus fx star, and this is less than equal to norm of x naught minus x star squared divided by 2 sum gamma I 1 minus 2 gamma I LB I equal 1 to t minus 1 plus sigma star b sum of gamma k squared k equals 0 to t minus 1 divided by sum of gamma I 1 minus 2 gamma I LB I equals 0 to t minus 1. There is one term left in the middle one on the right, which is xt minus x star, but that's a square of that, right? So expectation of xt minus x square, so this is positive, so I can drop this term because usually I don't want to see the t terms, right? So I'm always looking for a way to drop those. So this is greater than or equal to 0, and that's a negative. So if I drop that term, it still remains an upper bound. So that's why I decided to drop that, and we have this as a final upper bound. And then we will try to apply Jensen's inequality. Okay, so that's our and to apply Jensen's inequality, what we have to know is these guys are the convex combinations, right? So basically they sum to 1. Okay, these are the weights that sum to 1, and in that case I can take this inside F. Okay, so that's the step. So define Pk to be Ptk, okay, Tk to be gamma k 1 minus 2 gamma k Lb divided by gamma I 1 minus 2 gamma I Lb I equals 0 to t minus 1. Okay, so we have written a sort notation for this, and our goal is to take it inside F. So we observe that Ptk is greater than or equal to 0, and sum of Ptk equals to 1 for k equals 0 to t. Okay, so so we can now do the same thing we did last time, that we have expectation of x bar now, where x bar is defined to be weighted sum of with pk ptk, right? So with this we can stop. Okay, so this is the last line. So we have EB f x bar t. So we have taken so this x bar t is like p of ptk xk. Okay, so and then this is minus infimum. Okay, the way we write is fx star, and this is less than equal to, okay, f of the average is less than equal to average of the f. Okay, so that's the Jensen's inequality we have. So this is less than equal to EB of gamma k 1 minus 2 gamma k LB divided by sum of gamma I 1 minus 2 gamma I LB, and I equals 0 to t minus 1, and f x t minus f x star, and this is a sum over k equals 0 to t minus 1. Okay, so you get this, right? This is f of the sum of sum with these guys. Okay, so this is the same thing we did. If in case you want, you can see those video again. So this is the Jensen's inequality. F of the average is less than equal to average of the f. Since it's average, there is a sum outside. So so that's it basically. So which is eventually, like, the last line is just a breakup of this. Yeah, I mean this is less, and then eventually what we had was overall this guy was less. Okay, so the right hand side there is this, and now this is again less. So we can eventually write that this is less than equal to norm of x naught minus x star divided by 2 sum of gamma I 2 gamma I LB I equals 0 to t minus 1 sigma b star gamma k square k equals 0 to t minus 1 divided by gamma I 1 minus 2 gamma I LB I equals 0 to t minus 1. That's the final proof we had to do. So that's all we had to do for SGD, and all the analysis we had, all the recent results we had, 2021 results we had, all we did this. We can explore a little bit of momentum, but little bit, and then we will move to some other optimization methods. So that's all for today.